我哋教做 whip slap 噶嘛，咁可能你有少少 whip slap 喺度嘅，OK，即係咧 flat step 再加一部分嘅 whip slap 喺度，OK，因為 Hamilton 出得一條啫，咁我個 flat step 同埋會有少少 whip slap 喺度因為初頭預咗 Hamilton 出兩條嘅，但我問咗佢話出一條啫，咁所以咧就風你哋可以帶邊曲，咁Annex 你哋可以帶啦，咁好似係咪俾一張紙你帶啊？咁你帶一張紙啦，咁flat step 同埋 whip step 你當都有啦，因為如果唔係就係得兩樣有少少嘅啫，好嘛？咁你當有三條咁上下 ，OK， 加2個鐘頭俾你做，好嘛？
都會覺得如果真係你今日淨係講兩句關咩事啊？會冇關。好，你咁樣。星期六你哋得唔得啊？你覺得你想 online 上定話翻嚟 ？online 會好啲。但係你哋我記得點樣卡係咪？卡邊個星期六我哋火字啦。Okay, I think last time we mentioned about the whip slap, and then we mentioned that the waffle slap is actually the two-way whip slap. And then for the two-way whip slap, we have mentioned about how we can find for the answer. I think we mentioned about the way how to find for the moment, and then for the shear, we use this equation. Beta Sxn times Lx squared. And then we have Mxy beta Sy n times Lx squared. Lx is the shortest span of the slab. And then beta Sx and beta Sy is the coefficient. Depends on the span ratio, Ly over Lx. Okay, so we can find for the values for the Bx, x, and the beta Sy depends on the ratio of the length. And then for the shear as well, we can find beta Vx and then beta Vy, and then times n times Lx to find for the shear for the slab. Okay. So these are actually the values that we have found, and then this is the example that we are going to go through. So we are going to design a waffle slab for an internal panel of a floor system that is constructed on an 8-meter square module. And then the total characteristic dead load is 6.5 kilonewton per meter square, and then the characteristic live load or imposed load is 2.5 kilonewton per meter square. Then again, the concrete grade is C30, and then the concrete grade of concrete is, the steel is grade 500. Okay, so you can see that you have the width here. Okay, and then you have the width on both x and y directions, and then you can see that the spacing between the width is equal to 500 mm, and then the topping is 75 mm, and then the width depth below the topping is 200. So here we are going to design for the width slab. For here you can see that in the middle, actually the width is equal to 125 mm. That means between the slab, you can see the width is 125. But when it's close to the end, you can see there's a beam here, and then the width increases back to 500. That means originally the width is 125, but at the end, actually the width increases back to 500. The next one is here.通常尾個 moment 又大啲，個 shear 又大啲，所以咧臨近佢個 support 嘅時候咧，佢會闊翻嚟。OK。So this is the grip, and then this is the support beam here, and then when you close to the beam, then the width increases from 125 to 500. Okay, in this case. So you can see from here, it is 125 in the middle, but when you close to the end, it will get back to the width of 500. Do you mean what I mean? Do you know what I mean? So you can see that it is very thin here, but when it goes to the end, it has the full width here is equal to 500 mm. Sorry. Okay, so we are going to design a waffle slab like this， 即係佢中間嗰個 width 咧，全部都係120 mm 闊嘅啫。臨到去到尾差唔多俾條 beam support 住嘅時候咧，佢就放翻闊變翻500。點解咧？因為通常臨到尾呢個 shear 會大啲，嗰個就放翻闊啦，或者臨到尾個 moment 會大啲，所以我哋會放翻闊嘅。Okay, so for the arrangement of the slab, you can see that we have an arrangement like that, and then the cover, the phi is equal to 25 mm. And then for the loading, actually you can see that we have the dead load equal to 6.5 kilonewton per meter square. And then the live load is 2.5 kilonewton per meter square. So you have the design load equal to 1.4 times 6.5 plus 1.6 times 2.5. So your design load is equal to 13.1 kilonewton per meter square. Okay. Now for this one, you can see that it is 1 by 1 square. 8,000，另外嗰邊都係8,000，所以 it is 1 to 1, right? And then we say that this one is an internal panel, okay? So you will go back to this equation and then to find the coefficient. This is internal panel, right? And then you can go to this one, okay? One is the ratio between the longest span and then the shortest span, okay? So you have the coefficient here for the negative bending moment at the continuous edge is 0.031, while for the positive moment at the mid-span is equal to 0.024, okay? For the equation, we have already shown you use this equation, beta Sxn times Lx squared, okay? So for here, if you substitute the equations, then of course you will have 0.031, and then times 13.1, this is the values of n. N is 1.4 dead load plus 1.6 live load. And then times the distance, I mean the span squared. So the bending moment is negative 26 kN per meter. Because this is a square slab, so both the x and the y direction, the bending moment is the same, okay? So you know that at the ends it is supported by 500 mm. The slab width supported by 1 rib, because the rib itself is equal to, the spacing is 500, so the width supported by 1 rib is equal to 500 mm. So we have 500 here, which is actually the load width. So we will multiply this value by 500 because per meter we will take this load. Well, right now we have just 500 mm, so we have negative 26 times 0.5, and then we have 20.1 times 0.5. So the bending moment actually taken by the slab, taken by each rib is equal to 13.0. And then 10.06, okay? So again, we are finding the bending moment for a rib, just like the rib slab. Okay, we are finding the bending moment for the rib only. So you have the bending moment like this. And then, of course, you will have the values equal to 275 minus 25, this is the cover. And then minus the first layer, and then the second layer, okay? And then for this one, you can see that this is 275, it is the overall depth. You can see that this is the overall depth, 275. And then you will minus 25 is the cover. And then you will minus 6, this is the length. And then you have the first layer 12, and then the second layer 12 divided by 2. So you will have this 226 mm for the effective depth. So you will have this one, and again this one, and then you will have the 34, actually two colors. Now show you the length. So you have the outer D equal to 238 and then the inner D equal to 226. So if we want to use one reinforcement for both sides, of course we can choose D equal to 226. That is the most convenient one, okay? And then for the solid slab section, 500 mm wide, because actually at the end, the width will be equal to 500 mm. And then we have 13, because the bending moment is equal to 13 at the ends, okay? We say that the bending moment is 13 at the end. And then 13 times 10 to the power 6 over FCU B squared, which is equal to 0.017, okay? So K is okay. Then we can put this K to here, 0.017, okay? And then we can find Z over D is larger than 0.98, of course it's larger than 0.95. So we will put it as 0.95D. So the Z is equal to 215. So you have your moment divided by 0.87 Fy, and then this is the values of Z. Then you have these reinforcement values. And then of course we can provide two 12 mm bars. Then the area provided is equal to 226 mm squared. Okay. And then we can check the moment capacity of the width 500 mm away from the support. So here you can see that here is equal to 500. So we will check this section. So this section will be equal to 125, because here is 55. You can see that at 500 mm. Here, this 500 mm. So here
this width and then to 125 mm, okay? So this one actually will be like that. So you consider when you consider 125 mm away, so here you reduce to 125, okay? So the width originally is 500, but right here you reduce to 125, and then we want to check whether it will cause any problems to the reinforcement, or whether the section cannot be designed. So right here we will use the same equation, and then put the K values here, and then to find the set, and then to find the reinforcement. So actually it is still 114, so the reinforcement is still 2 T12 bars, okay? 嗱呢個 T 咧要擺喺頂嘅，因為佢個 support 嗰度係咪 ？So we will use 2 T12 bar for the support, okay? Is it okay? Because of the support, when the width is 500 mm, 2 bars is okay. When the width becomes 125, 2 bars is still okay. So we can put 2 bars on top to resist the and then the center of the span, then if you still remember, our bending moment actually reduced to 10.6 mm, okay? And then because in the center actually it becomes TB, so we can use a rectangular beam to design if the depth does not exceed HF, which is equal to 1075 mm. As mentioned last time, we are showing that the nucleus is set as the depth of the slab. Prime moment is just 10 or 06 kN, right? So if the neutral axis is at this location, then your bending moment is equal to 90 something. But right now your bending moment is just 10, right? So your neutral axis must be within the section. So your neutral axis will be within the beam, okay? Within the slab sections. That means you can use the rectangular equation. If the neutral axis is within this section, within the depth of the slab, So that's why we can use the same equations if the neutral axis is within the slab depth. Okay? So here we have shown that the neutral axis is within the flange or within the slab. So we can use the rectangular equation. Okay? So you have the moment divided by 500, this is the width, and then this is the depth, and this is FCU. So you have 0.013, and then for the moment arm it is 0.99, and then it is larger than 0.95. Okay. Then for this equation, you can get that Z is equal to 215. And then you have your moment divided by 0.87 Fy and then Z. Then you can get the area of the reinforcement is equal to 108 mm squared. And then that means you can still put two 12 mm bar right there. So at the bottom reinforcement, you can still put two 12 mm bar. So bottom, you can still put two 12. After checking the bending moment, then we can check for the shear. Then for the shear, we will use the similar way to find for the shear. So you have this equation to find for shear, okay? And then for continuous beam, you have 4 edges continuous. You have this one, okay, Ly over Lx. So you have the coefficient equal to 0.33. So 0.33 times N times Lx, which is equal to the shear force. So 0.33 and then times beta, and then times N times Lx, then that's the values for shear. So you have this one, and then you can find the shear is equal to 0.33 times N, which is equal to 13.1, and then times the L is the span of the slab. So we have the shear force equal to 34.58 kilonewton per meter. Okay? But you know that actually the rib is just support for 500 mm. 因為嗰個 rib 咧，佢只係頂住500 mm 咁闊嘅撈頂嘅啫。So you just multiply by 0.5, so it is equal to 7.29. Is it okay? This is the shear of the support. But what we consider is actually the shear which is 5 mm away from the support. So the width here actually is equal to 500. But we consider this location is the width point because the width is just 125. Okay? So we want to consider the shear actually 500 mm away from the support. Okay, so at the support, the shear is equal to 34.58. So this is 34.58. So we want to know the shear here, which is actually 500 mm. So what's the value here? So you can use this force minus W times L. Okay? So you can see that we will multiply 24.5 and then times 0.5, which is equal to 17.29. Sorry, 17.29. And then 500 mm away, then we can calculate minus 0.5 times 13.1 and then times 0.5
So actually it's equal to 40 on those two at this location. Okay? Because it is 500 mm away from the support, so we use this 0.5. And then this is the force actually due to the loading. So which is actually 13.1 and then times 0.5. 第一個0.5係因為佢由 support 行咗出0.5，第二個0.5係因為佢頂住個闊度係0.5。Okay? Do you know what I mean? So you may ask why there's two 0.5. The first 0.5 is that I step away from the support for 500 mm. So I minus 0.5. And then the second one is actually the loading. The loading is actually 13.1 is actually per meter. But your rib just support 500 mm. So I multiply by 0.5. Okay? So the shear actually 500 mm away is equal to 14.02 kN. Okay? And then you have this force, and then divided by the width, and then the depth. So the shear stress is equal to 0.47, okay? And then we compare this shear with the concrete shear strength, which is equal to 0.49, 0.79, and then 100 AS B over D, which is equal to 0.76 to the power 1 over 3. And then 400 divided by D, which is equal to 1.68, and to the power 1 over 4, and then concrete, and then divided by 25, and then divided by 1.25. This is the shear capacity of the concrete. So for this one, actually, it's between 0.5 VC and VC. So we will add the length, and then the length is a nominal length. In this example, they will add 6 mm diameter bar here. And then the reinforcement is equal to 250 kilonewton, grade 250. That means 250 Newton per mm square. And this equation is AS3, which is equal to 0.4 times the width, and then divided by the distance, and then equal to 0.87 times 250. This equation is the nominal length. Nominal length is PSV divided by S3, which is equal to 0.4 times the V times 2.7, and then times by this is the nominal length. Okay, so we just substitute these equations. And then we can find the spacing of the reinforcement. So you can see that we find that it is equal to 248 mm, but the distance has to be smaller than 0.75 D. Because we are assuming it is 45 degree crack, the spacing cannot be more than 0.75 D. And then the D is equal to 226, so we have 0.75 times 226, so it is equal to 170. Now originally, if in the real case, the spacing of the length should be limited to 150 mm along the rib. But in the book here, the notes is stated 160. It's still okay. But practically, when you go out to site, usually we will limit it to be 150 mm. Okay? 因為佢入會25 mm 跳一跳，咁你唔通常就唔喺地盤講得落嚟㗎啦。咁呢個係佢其中一個書嘅答案啦。咁我哋用翻佢個答案。Okay? But in practice, usually we will put 150 mm. Okay? Because we use 25 mm, multiple of 25 mm as the standard. And then for the diffraction, actually we will use the same way to check. So we have the basic standard ratio. This is, we assume that it's a continuous beam, okay? And then we have this M over BD squared, and then we can calculate the Fs. We use this modification factor equation. I think you know how to substitute. And then the maximum value is equal to 2. As this is 2.6, we will limit it to 2, okay? So the allowable one is equal to 21 times 2, so it is 42. And the actual span depth ratio is equal to 8,000 and then divided by 226. So actually it is equal to 35.4. So the allowable one is 42, while the actual span depth ratio is equal to 35.4. Is it okay? So the diffraction is also fine. For the topping, I think you still remember that we will usually put 12% of the reinforcement as the wire reinforcement in the topping. So you have 0.12, and then times 75 is the depth, and then we assume that it is 1 meter strip. So we will provide 90 mm square per meter, okay? So as what we mentioned before, the spacing of the wire should not be wider than half of the center to center spacing of the rib. And then your rib right now, the spacing actually is equal to 450, okay? Sorry, 500. So the spacing between the wire reinforcement should not be more than 250. 即係嗰啲鋼嗰啲鐵絲網咧，嗰啲鐵之間咧唔可以大。Okay. So for here we can still use D98 as the reinforcement. Okay, because the spacing is not more than 250, and you can provide the reinforcement actually more than 98 mm square per meter. You can provide 98 actually. So your reinforcement will be like that. The top reinforcement is 2T12, bottom reinforcement is also 2T12, while the shear reinforcement is R6 with a spacing of 160. Is it okay?即係咧，你嗰啲鐵咧係由 X 又擺 ，Y 又擺，然後啲 link 咧就沿住嗰啲 links，沿住嗰個rib 咧就擺滿佢 ，OK。If I take a look to this equation, I mean this figure, that means you have T12 bar in this direction, and then you also have T12 bar in the horizontal direction, and then your length is R6, and then the spacing is equal to 160 all along the ribs, okay? That is the reinforcement for the rib. 即係頂嘅位10年，底嘅位10年，全部都放 R6嘅咧個 space 嘅話，呢個 case，okay? Agree? Can you imagine the case? Because you have a rib, each rib you have 2 T12 at the top, you have 2 T12 at the bottom, and then you have plates with a spacing equal to 160 all along the ribs, okay? 咁啊做呢個帽係難啲嘅，因為佢要中間夾到個窿啊。咁我哋之前咧就用嗰啲膠管，一個個咧就笠喺個地盤嗰度。可能即係乾咗咧，佢就吹氣吹翻佢出嚟。Okay, so the single ribs, that is the one-way slab, and then the two-way slab, basically they have similar calculation method. But the most different thing is that the way how to get the bending moment. Okay? For this one, it is a two-way slab, so you need to use the table to get the two-way bending moment. Okay? And then depends on the ratio of the longer span to the shorter span. Okay. Okay, and after that, we will go to the composite slab and then go to the composite beam, okay? Well, actually, in the many tall buildings right now, they will use the steel beam, okay, as better arrangement. Why? Because the steel beam actually can give you a longer span, and they actually can give you a lighter structures. So usually they will use steel beam structures for normal tall buildings.
But for the slab, they still use the concrete slab, okay? So it becomes a composite is that for the beam section, it is a steel, but for the slab section, it becomes reinforced concrete, okay? So it comes to so-called a composite beam, okay? That means you have two different material. But before the whole beam is concrete, then you have reinforced concrete design. Or the whole beam is just a steel beam, okay? Then you have the steel beam design. But right now, the top is actually a concrete, but the bottom is a steel, okay? So it becomes composite. Composite means you have mix of material, okay? So this one, we call it the composite beam, okay? And then there are several ways how they can stick together. Now, usually they will use a shear stuck. Shear stuck, you can think of some, just like a screw, the screw is actually well on top of the structural beam, structural steel beam on the top. Because actually the concrete and the steel beam have to be connected together. They cannot be separated, okay? So they need to have some kind of shear stuck, and then well on top of the steel. And then when you have concrete cast on top, so that the concrete and the steel can stick together. 因為如果你諗下石屎還石屎、steel beam 還 steel beam 分開嘅話咧，你咬唔到佢嘅。你而家想石屎同埋 steel beam 一齊屈，你先做到 beam 嗰個效果啊嘛。但係如果你 steel 還 steel concrete 還 concrete，佢上喺上線嘅話咧，係做唔到個效果嘅。佢哋要一致先得嘅。咁你點樣保持一致咧？就係燒嗰啲我哋叫 shear stuck， 或者係個螺絲頭咧個頂嗰度，然後 cast 嘅時候咧。就將個石屎咬實咗個螺絲頭，咁咧石一屈嘅時候咧，石屎同埋 steel beam 係可以一齊屈嘅，咁先達到嗰個效果。Okay? So that is actually important is that you need to have a shear stuck so that you can connect the concrete and the steel beam together. Okay? Now usually there are two ways to connect. Sometimes you may just use a very flat bottom, and then you may have some kind of formwork at the bottom. So the depth is actually a flat situation. But instead, sometimes you will put some, we can call that this is the decking, okay, on the bottom of the slab. So basically, this is the way how they will okay, so maybe we just go here. So you can see that this is the reinforced, the structural steel beam below, and then at the top you have a shear stuck. And then here is the backing. The backing is actually placed between the beam and then the concrete directly cast on top. Now this backing usually will just place on top of the beam, and then it will not be removed. And this one, the backing is actually act as the formwork. And then when you place it, actually the workers can actually walk on top. And then finally,
It can act as the support, and then the workmanship actually can be done on the top, and then the workers will cast concrete on the top, and then do it easily. So you can see that here is actually the decking placed between the steel beam, and then you will cast concrete directly on the top of the decking. And then this one actually will act as the temporary support. The workers can walk on that and then cast concrete on the top. And then this decking will not be removed, and then they will stick with the concrete together as part of the reinforcement. 嗱咁佢咪快咯？佢將啲 steel beam 行晒喺度先。然後上面去鋪啲 decking， 然後咧板都唔使即係唔使釘板啦，嗰塊鐵嘅嗰塊 decking 就已經係埋咗個方位。咁咧佢個板咧已經係可以咧，即係人行上去夠力㗎啦。然後咧佢喺上面倒埋石屎，連板都唔使拆。Okay, then that is actually one of the way actually have been done in the Western countries for many years. And then in Hong Kong, actually, we also adopt this kind of way to cast the slab for some kind of composite structures, like the tall buildings, like the ICC, IFC, Chang'an Center, for example. They use this kind of way to cast the concrete. Now, of course, it is more expensive because the decking, they are proprietary products. We need to buy it from the supplier. It is more expensive. But actually it can support the self weight of the concrete and then support the self weight of the workers. And then the workers can walk on that freely. And then they can support the temporary load of the wet concrete. So actually it is a very convenient way for casting the concrete, and then it is very quick, can do it quickly. Okay, so you can see that we can just use the several ways to do that. Decking can be parallel to the beam directions, or if you turn it into 90 degrees, it can be perpendicular to the beam axis. So you can see that when we put the decking along the beam, it would be something like this. You can see there's a trough here. You can look at Lovejoy one, right? Or if you can put it 90 degrees, turning 90 degrees of the decking, then actually the decking will be something like that. And then the trough is in other directions, okay? So you can do it in both ways, okay? Depends on your design. And then for the steel beam, basically you can use the lattice girder. Lattice girder just like a truss, or you can use the composite castellated beam. That means you can see that the steel beam there has some hole within the steel beam so that your surfaces actually can pass through the holes, which actually reduce the beam depth, okay? That's the both way for you so that the surfaces can pass through the slab, pass through the beam. Now, one of the challenge for our building design sometimes is the surfaces, because the surfaces usually go under the slab. Of course, you can go under the beam, but actually will reduce the clear height of the building. So what we are going to do is usually we have an in situ hole there, and then you will pass through the slab, pass through the beam. That one is actually very challenging when you have a very large size of ventilation system. And then the duct size actually can damage the beam because it is so large that it nearly occupies the whole depth of the beam, okay? So you can use both ways to solve these problems. You may use composite lattice girder, or you can use castellated beam. So both are actually workable. Or sometimes they will use the steel beam and then with secondary beam on the top, and then you can see that you can leave some voids here so that the duct can pass through this kind of voids, and then
to serve for the purpose. And then to reduce the depth of the beam, sometimes you can see that this is the beam here, but this is the steel beam here. Usually this decking will be put on top of the steel beam. But if you want to reduce the size of the composite beam, actually this decking may sit on the lower flange of the steel beam, and then you can cast the concrete on the top. This is an alternative way for you to reduce the size of the beam. So they call that this is the slim deck system. So you can arrange it this way. 佢當佢坐喺呢一度，坐喺下面嗰條 flange 度。原身呢個 decking 要坐喺上面嗰個 flange 嗰度，佢就當咗佢坐喺下面嗰度，佢當佢 slim 咗。但係當然啦，個 moment capacity 都會細啲嘅。會，當然會啦。不過個 decking This is used when your headroom actually is very limited, okay? But of course, if your headroom is fine, of course, the decking should be put on the top of the steel beam, okay? Because you want to take concrete as the way to take the compression while the steel beam take the tension, okay? And then you can see that for here, this is the composite slab. And then the composite slab, actually you have the decking here, and then you have the concrete at the top, and then this is the steel beam. So the slab itself, actually you have the reinforcement on the top, and then the reinforcement of the decking, or I can say that the decking actually acts as the reinforcement of the slab. So for here, you can say that this kind of slab, you can call that as the composite slab, okay? 原身你撞 slab 咧就係下面係鋼筋。上邊咧就係石屎，而家咧呢個用咗個 decking 咧嚟做嗰個reinforcement，嗰個就叫 composite slab，OK？ But for this one actually there's a very rigorous design procedures for the composite slab. But instead of talking about the very rigorous way to define, we will introduce a simpler way. Actually, it is from the proprietary products design manual, okay? So we will mention that very soon for the composite slab. And then for the constructions of the composite beam, actually we have two ways for constructions. One we call it the plotted constructions, and the other one we call it the unplotted constructions. What does that mean, plotted and unplotted? That means if we put plotted construction, means all the all the loading will be carried by the plotting. Well, unplotted constructions means that all the loading will be taken by the steel beam itself. other way actually we have unplopped construction. That means we do not put any pockets below. Now if there is no opening, when I put the rack boundary on the top, what will happen? Actually, there's no problem in between, so the load will be taken by the steel beam. So there will be some direction here. Steel beam on the other side, okay? So this is the difference. Now you can imagine if there is
咁
no
放
opening,
大鏡睇放咗佢樣咯。
I mean, thinking about steel beam. Now, when the concrete harden, then the diffraction will be there. 係咪？因為砸咗落去嘛，到個石屎硬咗之後，佢依然係砸咗落去。Okay? But if there is pocket, then there is no diffraction in the steel beam, right? And then when the concrete harden, then there will be no diffractions. 係嘛？因為一開頭個 steel beam 唔使頂住嘛。咁你分開嘅時候咧，石屎同 steel beam 一齊 action。但係如果唔係嘅，你一開始冇頂住嘅，佢咪坐咗落去啊？咁佢咪有啲力已經落咗條 steel beam 嗰度。你再拆，等個石屎乾嘅時候，咁係咪所有啲力都喺個 steel beam 度，石屎冇飛出嚟？因為你一開始開住佢啦嘛，佢硬咗嘅時候都係保持住咁嘅狀態，都係嗰條 steel beam 成咗。Okay, do you know what I mean? The difference. Okay? So we have pocket construction. Pocket construction.
嗱永遠咧我都用呢個 composite beam 嘅時候咧，我就希望慳啲，唔想煩。如果都要 pop 嘅，同你傳統做石屎冇分別啊嘛，你都要加頂嘅，係咪？加頂有咩唔好處啊？要錢咯，要揾錢嚟租啲頂翻嚟啊嘛，係咪？仲要咩啊？要裝咯，要揾人去裝啊嘛，跟住咧要拆咯，全部都係錢嚟噶嘛。你要租，要揾人裝，要揾人拆，全部都係錢嚟。所以咧，如果你用 composite beam 嘅意思，我就盡量想唔裝拆。Okay, do you know what I mean? Because actually I can save the cost for renting the plopping, to install the plopping, and then to disseminate the plopping. Okay? So if possible, actually I want to use unplopped constructions, actually to 個時間又慳翻咧，係咪？所以你唔 pop 嘅話，時間又慳，錢又慳，係咪？咁所以咧，盡量我哋都想用 unplopped construction。OK？嗱 ，for this one actually， 而且你下面又慳翻啲位咧，你下面封晒啲位，你行到嚟行唔到機，所以好多原因點解我唔想 pop。And then for here you can see that actually I need to have extra cost, and then I need to have clear space for those kind of things. But if there are lack of the space, lack of money, lack of time, of course we will not plot anything. And then actually the final diffractions will be the sum of the diffraction of the steel beam during constructions, plus due to composite action, due to the loading.
This is actually direct loading. Okay, so we have for this one actually I removed the loading actually there's no diffraction. Because after the composite action, only there's the loading at the composite action. That means concrete will take compression in the steel tension. Okay? Then for this construction stage, of course, this one let us see okay? And then when the concrete hardens, then there will be another diffraction, okay, due to the composite stage, okay? So this is the construction stage. total diffraction is actually just due to the composite performance of the space, okay? Because all the diffraction is during the composite stage of the beam. So for here, the total diffraction will be the stage construction stage plus the delta and composition stage. Okay? So you have the diffraction, overall diffraction. 因為呢個咧石屎係硬嘅時候，佢甩咗落去啦。而石屎硬咗嘅時候咧，你再加其他屋景落去咧，會再 further diffraction。咁啊兩個 diffraction 加埋。OK？ 而呢個咧喺石屎未硬之前係直入係冇 diffraction。喺石屎硬咗嘅時候咧，佢先至開始係高嘅，所以呢個 diffraction。So you need to address the diffraction, one without plopping and one with plopping, okay? And the stress stage is also, because the one without plopping, then the beam itself will be at the load, right? So we have the so-called the lock-in stress. So the stress will lock in the beam，永世都喺嗰度啦，出唔翻嚟點解？因為佢已經砸咗落去，令到佢個 banding 嗰度永遠都砸唔到啦。OK？ 呢個 loading 佢個石屎，因為佢微光嘅時候咧，淨係得條燒邊棘啊嘛，得條燒邊棘晒。But for this one there is no loading stress because all the stress, all the loads will be taken by the plopping. So there is no loading stress here, but here there's loading stress, and then due to the composite stage, concrete and the steel beam they work together, so this is that one here. Okay, this is the composite stage, this is the loading stress. So the overall stress is the loading stage plus the overall stress. Okay, so this is the steel beam, and then this is the concrete. So this is the loading stage. And then this is the composite stage. What I mean? Because due to the construction stage, the steel beam itself will have stress, compression, and tension. And then after the concrete part, then you have overall composite stage. That means the whole section will bend together. So your stress will be this one plus this one. Okay? I just show you quickly the stress diagram, which is actually later. You will see that it's something like this. In construction, you will have the stress like this. Okay? And then during the composite stage, you will have something like this. So the overall is this one plus this one, so the overall stress stage is something like this. Okay? So this is the so-called composite stage. I mean, without plopping. 因為你一開始嗰條鐵自己上到嚟先，等石屎硬咗啦，石屎同 steel 一齊上嚟，咁所以佢哋一齊 bend。OK， 一個係 steel 自己 bend 嘅先，然後咧就 steel 同石屎一齊 bend， 然後就將呢個加埋先至係最好個。如果你本身開始有 plopping 嘅話咧，呢個係冇嘅，因為條鐵唔會自己上嚟，任何嘢都俾個 plopping 做咗。咁你一掹開 plopping，你再加 load 嘅時候咧，佢就得呢個嘅啫，有分別㗎。OK。有當有人喺上面行，因為喺上面行，另外人喺上面行，佢都只係有 composite。如果佢係有 plopping，只係出現呢個，呢個唔出現，因為佢唔會有一個情況單個 steel 自己係高嘛。你可以當有啦，即係你就算當冇咧， 佢如果佢係 plot the case 嘅話咧，任何情況石屎同鐵都會一齊剔力，因為你唔存在住淨係得 steel beam 剔力嘅情況嘛。OK， 但係如果你係 unplot 嘅話咧，一開始只有 steel beam 剔力，所以佢就有個 stress 係 lock in 咗入去個 steel beam。你明唔明我意思啊？一開始石屎未硬啊嘛，淨係得 steel beam 啊嘛，咁咪淨係得 steel beam 剔咗個力咯。到石屎硬咗啦，我哋一個叫 composite stage， 石屎同鐵一齊剔啦。你再有任何嘅 loading 加上去嘅時候，就係用 composite 嘅方法去剔啦。但係如果你有 popping 嘅話，石屎由始至終都係唔剔力嘅。sorry， 即係鐵都唔剔力嘅。到石屎硬咗啦，石屎同鐵共同承擔所有指引嘅 composite。OK，you know the difference。以後咧，你哋出去做嘢咧，佢而家好興玩嗰啲 Pcast 嗰啲嘢，尤其是咩 MIC 嗰啲都係。佢有啲石屎係先 cast， 有啲石屎係後 cast。OK， 所以咧，先 cast 嘅石屎咧係好似個殼咁樣，所以咧喺後 cast 嘅石屎未硬之前咧，佢哋係會承受一定嘅 loading 先嘅，因為之後嗰啲石屎未之前嗰啲石屎硬咗，之後落嗰啲未硬啊嘛，咁即係佢剔唔到力啦。先落嗰啲石屎咧就會剔住個 cell weight， 所以佢哋成日有啲 lock in stress 喺啲 cast 嘅 concrete 入邊。到出邊嗰個石屎，到你換落嗰個石屎都硬咗啦，佢咪變咗個正體啦。嗰時再加啲 loading 就一齊嚟啦，所以成日都有 lock in stress， 再加 overflow stress。你第時出去做嘢就會見到好多啦。咁就好煩。
有杯，有海報，有鎖匙，有隻電話繩。
And the composite actually will have this one， 因為而家出邊好多時中意做嘢咧係落咗個殼先，然後咧再喺入邊再灌石屎嘅，尤其是你哋做嗰啲 MIC 咧係會咁做嘅。佢先有個 Pcast 先做，再入邊再配鐵再流落。
超細化。
OK。
呢個額外俾，唔係呢個另一款嚟嘅貼紙。
因為咧而家咧佢哋未必用板㗎啦，佢哋先
跟住我呢張其實
做咗個殼先，
抌一塊嗰啲佢咪有啲碟轉嚟轉去嘅，嗰啲廣告啲碟上面叫雲咁嘅蠟燭。
做好多而家好中意用石屎嘅 MIC
呢張我得兩張。
咁多人有鐵嘅 MIC 同石屎嘅 MIC。
但我想講佢襟章係唔夠咯，佢襟章，佢襟章就要攞5張呢一個去換咯，佢個襟章要攞5張呢一個去換咯，係啊，對抽38蚊一碟，跟住佢攞5碟，
跟住我哋當佢受個面係，
我哋當佢做咯，跟住仲要抽咯，換咗佢，
cast 得好好㗎啦，我哋當佢呢一個 section。咁當然佢穿晒鐵嘅，我開上去聽，佢話呢度有個扣出嚟。然後咧中間有嚟㗎嘛，穿條鐵可以咁嚟拆去，咁跟住再穿翻兩條鐵。
喊撚中個背就係喊撚咗。
係啊，全部係香港特有研究出嚟嘅。初頭唔知點做，大佬你咁拍到咁埋，你點穿鐵咧？做唔到啊！有你研究咗個新嘅方法出嚟，先貼落去先。跟住咧喺嗰啲扣嗰度一擰過去，咁另外嗰個扣就搭實過去。係啊 ，Richard 啲嘢，佢哋諗啊嘛。嗰次 structural division， 佢哋 present 嘅時候我就聽到。OK， 嗱 anyway，so I just introduce you this so-called the lock-in stress and then we have the overall bending stress。OK。而家嗰種 MIC 咧就越諗越複雜。初頭咧，佢哋嗰個盒咧，即係你知其實佢一個盒仔啊嘛。佢嗰盒仔咧，佢就唔當佢個腹窩咧係 structural wall 嚟嘅，佢就當佢自己一腹窩。而家咧就玩到咧，要將嗰啲MIC 嗰啲盒仔咧，嗰啲窩變埋 structural wall。佢係想薄啲啊嘛，因為以前唔計嘅話咧，就好鬼厚，因為你自己 structural wall 要一塊窩，另外嗰兩個盒仔嗰塊窩又分開嘅，咁你成個 structure 咪好厚嗰腹窩。因為嗰兩塊係當 structural wall 嘛，佢係想減輕個幅 structural wall 唔好咁厚咧，就玩埋嗰個 MIC 嗰個盒仔個腹窩要變埋做 structural wall，咁就好煩啦。因為你要諗住佢哋即係要 cast 得好嘅話咧，
我見過份 prelim 數計咧，
好厚咯。
佢個 lift core wall 要去到米，
係啦，好厚咯。佢
米
係我哋係承擔唔到啊。咁所以咧，佢哋而家就一定要用埋嗰個 P 卡，即係用埋嗰個盒仔，用埋嗰個盒仔嗰個窩嚟做嗰個 structural wall 先得。香港咧玩 MIC 都玩得幾刁鑽。Okay, then for this one actually I just would like to introduce you I just mentioned about the deflections, okay? Now for the composite slab, as I mentioned, there's actually a rigorous way in the scope of practice to design the moment capacity of the composite slab. And then, but that one actually is more complicated. But here I would like to introduce you the load span table, usually provided by the supplier. 如果你喺公司做咧，有時咧有啲 engine 咧會拖住個篋仔上嚟咧，就同你 sell 啲 product。咁咧呢啲咁樣嘅我哋叫做 proprietary product， 即係啲公司嘅產品咧，佢自己通常有 design manual 嘅。咁佢哋就冇一個 design code 咁複雜，佢哋咧就用一個load span table。佢話俾你聽咧，應該用幾厚嘅呢啲咁樣嘅 decking 就得啦。咁我哋咧就會同你講呢個。咁曲嗰個咧，因為佢計完之後其實個 capacity 太低嘅，咁所以咧我哋 instead 我哋就同你講呢個。OK。So this one actually has been used by many suppliers. So you can see that they will usually mention about the decking, the depth of the decking. Okay, you can have this one actually is what is the thickness? Okay, 0.9 mm, or you have 1.2 mm. Okay. So for this decking, this is one type of the decking. So you have the 1 hour fire rating, 1.5 hour or 2 hour fire rating. And then the slab depth actually is varying from 125 to 250 mm. And then for the mesh, actually you need to put the mesh within, actually it is for fire resisting, okay? Because when you have fire, then the bottom decking will be softened. 即係你底嗰塊 decking 你俾火燒嘅時候咧，佢會腍咗嘅。咁所以咧，另外咧要加啲鋼筋咧去做嗰個叫 fire reinforcement。如果唔係咧，你冇鋼筋嘅話，佢會散㗎嘛。即係石屎唔可以冇鋼筋嘅。So for here, actually, it is for fire resistant. For this one, you can see that the decking, if the deck is 0.9 mm, that means it can withstand a span for 3.2 meter. And then the applied load is 3.5 kN per meter square. If the load is 3.5, then it can withstand the span equal to 3.2 meter. If it is the fire rating is 1.5 hour, then it can withstand a span of 3.1. And then here, if the slab is 150 mm, then it can withstand a span of 2.9. So depend on your loading, and then depend on the span between the beams. So you will choose different kind of depth here. So this is 5, this is 10, this is the design load, okay? And then depends on the design load, and then depend on the fire rating, depends on the span. Actually, you can choose either 0.9 or you can choose 1.2 mm as the decking being used for your case, okay? So this is the way we want to show you. Actually, you will have this kind of so-called typical load span depth table. And then this is actually for different product, and then this one actually is for products of Taurus, okay? This is one of the brand. Then this is for the normal weight, grade 35 concrete, okay? So 呢個係你個 design load，咁當然你計石屎嘅 load 梗係要計埋啦。呢個係你個 apply load，total 嘅 apply load。你石屎個 depth 就已經係有呢個啦，你喺上面加嘅 load。呢個 apply total apply load 嘛，即係佢哋 total 嘅 apply load 梗係要計埋個石屎 load。
有個 working load， 有個1.5個 kilonewton per meter square， 一陣間會有 ，OK。But for here you have different sections, okay? So you have the re-entrant, trapezoidal, and a deep deck. So this is a different arrangement for the decking, okay? So you usually with a table, and then we'll show you what's the depth, and then what is the span and the loading that it can support. But for the composite beam design, actually we have the several procedures. Now actually we will treat the composite beam as a T-beam, okay? So you will have an effective brief BE here, because actually we will treat the concrete as the top of the T-beam, and then bottom we have the steel beam, okay? And then so this actually is the BE. So for slab spanning perpendicular to the beam, so the effective brief BE is actually equal to the span divided by 8. So if you have the span and then you divide it by 8, actually it is equal to the effective width of the beam. And then of course, if the slab spinning parallel to the beam, it is still LZ divided by 8, so both of them is the same. But this one has to be more than or equal to 0.8. While B is actually the center-to-center spacing between the steel beam, okay? So basically, you just need to use the span divided by the 8 that you can find for the effective width of the T-beam. So if you can see that this is actually on the left-hand side, this is on the right-hand side, so this is the effective width of the beam. So you can see that this one actually is just like a T-beam, okay? So you have the top of the concrete taking the compression force, while the I-beam below will take the tension, basically. And then you can preliminary your size by using span divided by 20 for the span depth ratio. This is for the concrete. We use the basic span depth ratio. Actually, we can use the same way to get the preliminary size of the steel universal beam, okay? But I think you just mentioned about during the construction, what is the construction weight, okay? But here in Hong Kong, actually, we assume that the imposed construction load is equal to 1.5 kilonewton per meter square. Okay, so this is the construction weight. It is actually assumed the workers, which actually and the equipment actually put on the top of the slab. And then if the span between the section is less than 3 meters, of course you can increase the loads by using 4.5 divided by LP. Okay, you just if LP is the span between the slab, you can see that if it is equal to 3, actually it is exactly equal to 1.5. Okay, so normally if the span exceeds 3 meters, actually we will assume that the working load is equal to 1.5 kilonewton per meter square. 即係話咧，你喺個陣上邊咧，即係卡石屎嘅時候咧，你可以當個 working load 咧係1.5個 kilonewton per meter square。Okay， 1.5個 Newton per meter square。And then the ultimate limit state, of course, the shear, actually the beam itself, because we assume that it is not the case. So all the loads has to be taken by the steel beam. 我哋冇 plot 嘛。落石屎嘅時候咧，所有嘅力要係俾嗰個鐵嘅邊個的晒。So for this one, actually we need to check for the ultimate limit state for both bending and shear. And actually we also need to check for the serviceability limit state. That means we check for deflections. So for here, we can take a look to the bending and shear for the composite section afterward. Because during construction, of course, the loading is just taken by the steel beam itself, okay? But after the concrete hardened, so both the bending and the shear will be taken by the composite section. That means concrete and the steel beam, they will work together. 即係佢硬咗之後咧，
你再加啲 loading 咧，就會係石屎同鐵一齊剔㗎啦。OK。So for this one, actually you need to take together. And after checking the so-called composite actions, and that means the moment capacity and shear capacity is fine. The next one you need to check is for the shear connections. 頭先我咪講要加啲螺絲頭嘅，咁加幾多粒咧？幾唔超一粒咧？ So we need to check for that one to make sure that the concrete and then the steel beam they will stick together and then act together. So that one is important that you need to calculate how many shear stuff to be installed. And then actually there are two ways to transfer the moment. One we call it the full shear connections. That means we provide enough number of shear studs, or we can use partial shear connections. That means we provide less shear stud than the full shear connections. 嗱，如果我哋 provide full shear connection 咧，就完全發揮到嗰條邊嘅功效嘅，即係我完全 mobilize 到個 full capacity 出嚟。但係你知啦，有時候個 loading 咧就唔係咁大噶嘛，咁我唔使發功發到100%，我發到80%都夠啦。咁我咪落啲 shear stud 落到80%咪算咯。OK， 即係殺雞用牛刀係咪先？我一巴冚死你嘅，所以用隻手指尾都搞掂你啦，係咪？我殺雞用一巴去冚你。So that's actually I do not need to mobilize the full moment capacity. I just need to mobilize some of the moment capacity. Then actually I can take the loading that I want, right? So I can put less shear stud so that my moment capacity is good enough to resist the bending moment. Okay? So I will introduce to you what is full shear connection and what is partial shear connections. And then we also need to check the bending and the deflections at the serviceability limit stage. That we must take a look to the deflections at the serviceability limit stage, whether it is okay or not. Because of course the moment capacity is fine, the shear capacity is okay, but we still need to check for the deflections. Okay. Okay, then the first step, then we can take a look to the steel beam when it is under constructions. So we have now the unplotted constructions. Right here, first of all, we will put the loading equal to at least 1.5 kN per meter square. Then the moment capacity, I think you still remember that is the Py times S, which is actually equal to the moment capacity. 大家有冇印象？呢個 steel beam 如果我能夠變成 plastic hinge 嘅話，我係點樣揾個 moment capacity 啊？係將個 shear sorry 係將個 design strength 乘乜嘢啊？乘翻個 plastic modulus 有冇印象？ So this is actually the very basic assumption is that you assume that your beam can form a plastic hinge or you can have the yielding in the section. Then you just use the design strength of the steel, which is equal to Py, and then times S. S, we call that the plastic section modulus. Just Py and then times S, then we can get the ultimate moment capacity of the sections. 嗱，首先remind 下大家先，記唔記得 steel section 咧有四個唔同嘅 section 㗎 ？Class 1、Class 2、Class 3、Class 4有冇印象？有冇印象鐵有呢4種 section？ 你 design 條 steel beam 嘅時候 ，why we have different 4 sections? Because one actually I can form full plastic hinge. 我可以咧成條陣都腰晒嘅，由個邊一路腰到落底嘅，可以行好遠嘅。OK。Class 2 I can still form a plastic hinge, but I cannot go for a very long distance. Class 3 just top and the bottom can get yielding, but in the center I cannot get yielding. And then section 4 is actually my beam cannot yield, it will buckle. 我屈下嘅時候，佢就 buckle 咗，佢都未 yield. So I have 4 different kind of sections, if you still remember. If you don't remember, it doesn't matter. You can always go back and then to take a look to revise the steel design. Okay? But it is very important actually for you to define whether your steel section is class 1, class 2, class 3 or class 4, okay? But usually if it is a universal beam, do you still remember we have universal beam, universal column, universal pile? 記唔記得你嘅 steel section 呢樣嘢 ？Universal beam, universal column, something like that. Actually, you can check from the steel table. Then there's some standard section. We call it universal beam. Okay? Those universal beam is actually class 1 section, so you don't worry about that. All of them can get yielded. Okay? These are class 1 sections. So when you have class 1 section, then that means you can have Pys and then times S, then you can have your moment plastic capacity. Okay? So you just have the Py, that means the design strength and then times S, then you can get your moment capacities, okay? And then for the shear capacity, just remind you that you know what is the yielding of the reinforcement. But what is the shear capacity of reinforcement? 鐵成日都知佢 yielding 係幾多啦，但係鐵嘅 shear capacity 係幾多？石屎你可以查佢一個 VC 係咪？咁鐵嘅 shear capacity 係乜嘢咧？記住啦，同個 yielding 係有關嘅，乘0.6嗰度就得啦。0.6乘個 yielding 就係個 shear capacity。OK， 好容易嘅啫，佢500 T 乘0.6就係個 yield strength。OK， 大家記住啊，呢個唔難嘅，記住就得啦。OK，for the shear of the steel，OK，just 0.6 times the yield strength, then there's the shear strength, okay, for the steel beam, okay? And then usually for the steel beam, we just take the T and D as the shear section. Always just time the strength times the width of the web and then times the overall depth of the section. This is the shear capacity of the steel beam, okay? So just remember these kind of things, okay? So it's important. When you go to work, you may not remember everything, but for this kind of simple idea, I think you have to memorize it. 起碼你人哋問你喂個 moment capacity 點揾啊？steel beam 一樣又唔知喎，石屎我知，石屎我成日都知道咧。用個 moment 啱乘翻下知，到 steel 我又好似唔係好記得喎。記住用個 plastic modulus 乘翻個 yield strength 就係啦，0.6乘翻個 yield strength 就係 shear。咁個 shear 咧永遠就係靠個 web 嘅啫，頂底下面嗰兩塊咧係我哋 take moment 嘅 ，shear 就係靠打戙嗰塊。其實個 direction 已經話咗俾你聽 ，shear 通常打直㗎嘛，咁打直嗰塊呢個係嘛 ，moment 靠 compression tension 啊嘛，所以咪頂底嗰兩塊咯，得唔得？咁樣記住就容易啲記住 ，OK。So this one actually just shear because you just it's vertical direction, so just the vertical part, the web part will take the shear, and then for the bending moment. Because you have compression and tension, right? So the top part and the bottom part will help to take the bending moment, okay? So just use this simple idea. You can always memorize the importance of the flange and the web, okay? And then for the serviceability, usually we will have the equation for here to check for the deflections. It is 5WL to the power 4 and then phi 84EI 嗱呢條 equation 咧成日都你成日會見到嘅。呢條 equation 咧係幾時咧？係有條 simply supported beam，然後你個 distributed load 嘅時候咧，佢中間嘅 deflection 係幾多 ？OK？ 成日都見到噶啦 ，Mova 384呢個咧，如果你記到咧，你就記咗我哋成日都有，成日都出現嘅，成日都問你個 deflection 係乜嘢，成日都出呢條 ，OK。咁 Mova 384 WL4 Forward EI 試下啦嚇，試下記唔記到啦。咁咧，任何式個 deflection 都用呢個啦。Composite 嘅困難喺邊度咧 ？What is the difficulty for the composite to find the deflection? Is that we know 5, we know 384, we know W, we know L. But for E and then I, that's the difficulty. If it is a pure steel, you know the Young's modulus of steel, and then you know the Young's modulus of the I. Okay? If it is a pure concrete, you know the Young's modulus of the concrete, you know the Young's modulus of the I. But if it is a composite, you have concrete and steel, and then the I, you have concrete, and then you have steel in I. Then how to find EI? That's the questions. 如果你純粹係石屎，簡單啦，石屎嘅 Young's modulus 加石屎嘅 I 就得。你純粹 steel 嘅 ES 再加純粹 steel 嘅 I 就得。你而家有 composite， 你點解決個 E 同埋點解決個 I 咧？所以咧呢、這個就係即係要同你分析嘅地方。因為你唔知個 E 係點樣計啊嘛，因為你有石屎有鐵一齊啊嘛，咁你攞邊個 E 啊？咁你個 section 上面石屎下面有鐵啊嘛，咁你個 I 點計？係咪仲係攞 BH3 次除12？咁呢個咪要 discuss 嘅地方。OK， so this one actually is the thing that you need to know. If it is pure steel or pure wood or pure material, it is simple. Okay, but when you have composite of the material, how can you solve these kind of questions? Okay, so you need to think about that. And then when you have the sections, of course you have the moment, and then you have the so-called elastic modulus. When your section is still in elastic stage, we have M divided by Z. So the top and the bottom stress actually is moment divided by the so-called elastic modulus. It becomes a stress on the top and then the bottom. Okay. So this one actually is an easy way to find the stress. This actually comes from the bending stress equation. So this is actually recorded the elastic modulus. It is actually I divided by 1. I think you learn all these kind of things during your structural mechanics or mechanics of material. Okay, I'll just give you some memory to refresh your mind. Okay, then we will go for the first example. Then for here, check the strength of the universal 4, 5, 7, 1, 9, 1, 74 steel beam here. 嗱，呢三個數字喺個 steel beam 度代表乜嘢啊？其實咧呢個咧係其中一個考牌，我哋都問過你。咁咧佢嚟過我哋問啊，你通常 steel 有三個數字嘅噃，第一個數字、第二個數字、第三個數字係代表乜嘢啊？咁你過咗關啦。咁咧，我哋問佢第一個數字，應該都係同高度、深度同闊度有關，咁佢都答到嘅。第三個數字佢答唔到。咁咧，我哋就即係冇俾個牌佢啦。係啦，咁你知唔知啊？第三個數字係代表咩 ？kg per meter。OK， 咁你知道咧，起碼咧呢條問題你搞掂咗啊，咁就唔會俾呢條問題阻止咗，一定攞唔到個牌。但係有同學真係唔知嘅喎，即係佢做咗幾年嘢之後咧， 或者調翻轉講啦，佢讀緊書嘅時候可能知嘅，佢做咗幾年嘅時候唔記得咗，咁咧就咁佢又冇咗牌 ，OK， 或者出年翻嚟做效果 ，OK。嗱 ，sometimes actually the question during the interview is not difficult, but 有時我係諗住益佢，點知係害咗佢。咁咧就好似咁樣，我哋諗佢實識答㗎啦，咁點知佢答唔到，咁更加我懷疑，佢原來佢咁都唔知，咁咧就OK 嗱 ，anyway， then this actually actually this is the depth, and then this is around the width, and then this is the weight, okay? And then the PY is actually this is the design strength of the steel, and the S is the plastic modulus, 1653 cm cube. And then the beam, this one span 12 meters, okay? And then you can see that the concrete flange itself is 3 meters, okay? This is 3 meters. Actually, it is the span of the beam, and then divided by 8. This is, we call it the effective width of the beam, okay? So you will take the load here, and which is actually equal to 3 meters, okay? But for here, how can we check for the steel beam? So you can see the average depth of the concrete slab and the width. You can see that you have the width here, and then the depth is equal to 90, while the trough here is equal to 50. So you have 90 and then plus 50 divided by 2. So you want to check what is the average depth of the concrete here. So this is 90. 90 is actually up to the top part, 即係由個頂去到呢個 trough 嘅頂。咁咧就係90，咁呢個 trough 咧係50深啊嘛，咁我哋攞一半，所以咧就係90加50除2 ，OK。
240蚊，3隻。
因為佢一半係
唔係佢原價都係80蚊嘅喎，不過我唔要呢隻，我中意紅色嗰隻。
And then the weight of the concrete is actually equal to 0.155 and then times 24. Okay.
拉環啊！
嗱，if you go to exam, now you can either put 24 or 24.5. It is acceptable. Okay. So it doesn't matter. Right here, the calculation they put 24, but if you put 24.5, it is still acceptable. Okay. And then you have 2.76. This is actually the weight of the concrete. And then this, the steel deck, we assume that this steel deck is equal to 0.15 kN per meter square. For the steel beam, here is equal to 0.24, because you can see that this is 74 kg per meter, right? So if you have 74 and then times 9.81, and then you divide it by 3, you can find for this value. 你睇唔睇到呢個0.24嘅 kN 啊？點樣出嚟咧？呢個係咪有74咧？就係佢本身呢個重量係咪？74乘9.81係咪個 total 嘅 load 啊？除翻3，因為佢除翻呢個闊度係3米係咪？咁你就會計到佢係0.24個 kN per square。Okay, you can try that. You can use 74 and then times 9.81 and then divided by 3. Okay. Then you can find for this value. Okay? And then if you add these, the concrete load and then the deck load and then the steel beam load, you will get the deck load is equal to 3.15. And then remember, you have the live load is equal to 1.5. So you have 1.4 times the deck load plus 1.6 times the live load. And then the width is equal to 3 meters. So you have 20.43 kN per meter. This is the loading, okay? 因為個 loaded width 咧係3米 ，OK， 咁所以咧佢加晒個 loading 落嚟。Then for this one, you can see that the maximum bending moment is WL squared divided by 8. So you have this W times the length divided by 8. So you have the bending moment is equal to P68. This is the maximum bending moment. Now, the moment capacity of the beam is S times Py. S is 1653, and then the Py is equal to 355, and then you divide it by 10 to the power 3. So you have 587 kNm. So your moment capacity is equal to 500 something, while your moment, applied moment, is equal to 368. Okay, so your moment is fine. And then for the shear, you have the overall depth is equal to 457, and then the maximum shear is 20.43 times 12 divided by 2. So the overall length is 12, and then you divide it by 2. So the shear force is equal to 122.6. And then for this capacity, you can see that it's 0.6 times Py times Td. So you can see that the capacity is x76 kN, while your applied load is 122.6. So both the moment capacity and the shear capacity is satisfied. Okay, so no problem. So this is the checking of the steel beam during the construction stage. That means the steel beam is okay. Okay， 即係條 steel beam 我嚴格確定都冇問題，因為個 moment 係冇 OK 嘅，個 shear 都 OK 嘅。個 deflection 我哋唔 check 住，一陣間我喺最後嗰個 section 先 check 佢個 overall 嘅 deflection。但係其實你要 check 嘅，即係等唔好過秒啊嘛。但係咧我哋留翻喺一陣間最後嗰個 check。So for the moment capacity, actually, as I mentioned, it is a composite action between the concrete on the top and then the steel on the bottom. Okay? So if we consider the total load in the concrete, actually it is equal to 0.45 FCU. This is the concrete strength. And then times the width BE, so the width BE is here. And then times ds minus dp. ds is the depth of the slab, and then the depth of the trough is actually dp. So we just consider the concrete on the top part. 即係話咧，我想睇下個 concrete 受個 compression force 係幾多 ？0.45 FCU times BE and times ds minus dp. So this is the compression force in the concrete. And then the one here is actually the tension force in the steel. So actually it is Py times A. So this is the Py, the new strength of the steel, times the area of the steel beam. Okay. Now for the others, actually it is actually the force in the flange, and then the resistance or the force in the web. Now I don't go through one by one, but I just let you know that RC is the concrete, RS is the steel. Okay. RCX is actually the concrete force, and then if the neutral axis is equal to X, okay, then I have the concrete compression forces here. Now, and then for the case, actually I will derive the case in 3 different scenarios. One is actually the neutral axis is in the concrete flange. The other case is the neutral axis in the steel flange, and then the neutral axis in the steel web. Actually, the moment capacity is a bit different. It depends on the location of the neutral axis. If the neutral axis is between the concrete, then we use one equation. And then if the neutral axis is other location, we use another equation. So basically, we have our neutral axis would be a concrete section. Okay, this is the first situation. The second situation is the neutral axis is between the flange. This is the second situation. The first situation is that the neutral axis is between the web factors. So this is between the concrete flange. And then the second one is between the steel flange. And then this is between the west. Okay. So I have 3 different situations. Is the location of the neutral axis. Okay.
So you can see that the neutral axis here is within the concrete flange, while here the neutral axis is within the steel flange. And then the final situation, actually the neutral axis is within the steel web. Now you can see that if the neutral axis is within the concrete flange, the top part here is compression. So this is the concrete compression. And then below actually all of them are steel. So the whole steel actually will be in tension. So you can see that you have concrete compression at the top, steel tension at the bottom, and then you multiply with the moment arm. So this is the moment velocity. Set C, heat compression, in the heat tension. Compression and tension 加埋成翻個 moment arm 嗰就 moment velocity。OK， 但係以前咧concrete 嘅話咧 ，concrete heat compression tension 係靠個 steel bar 嚟嘅。呢度咧石屎都係 heat compression， 但係 tension 咧就靠個 structural steel 嚟嘅，就唔係個 steel bar。所以咧有啲唔同。OK。For this one, actually, the neutral axis is within the flange, the steel flange here. Okay, so the concrete itself is in compression. Part of the steel is also in compression, and then the remaining part of the steel is in tension. Okay. And then for the final case, actually, the neutral axis is within the web, so you can see that part of the section, all the section of the concrete is in compression. And then of this part, actually the neutral axis is here. So part of the steel section also in compression. And then part of the section of steel is in tension. 即係個 neutral axis 咧唔同位置嘅時候咧，就令到可能 steel section 啲位置都會受限。OK。Then how to determine the location of the neutral axis？ 咁我點知個 neutral axis 喺邊啊 ？neutral axis 咧其實唔難揾嘅，永遠 compression 等於 tension 咧就係個 neutral axis 嘅位置啦。你明我意思啊？永遠因為條燒邊嘅話，即係 tension 同 compression 永遠要係一樣。咁揾到嗰個地方一樣，個 neutral axis 就喺嗰度啦。即係你個 neutral axis 界到喺嗰個地方嘅話。compression 等於 tension 咧，咁個 neutral axis 喺嗰度。OK， 因為佢個 beam section 嘅話，佢個 neutral axis 佢個 compression 一定要等於個 tension 噶嘛。你個 neutral axis 擺到嗰個位 ，compression 等於 tension 就喺嗰個位置。OK， so here you can see that if the concrete is very strong, RC is very strong and then larger than RS, then you cannot make use of the full section of the concrete because if you make use of the full section, then it will be larger than the overall tension within the steel. So the neutral axis must be within the concrete section. 如果你用晒成個 concrete section 咧，個 compression 係大過 steel section 嘅 tension， 咁即係話其實你唔可以用晒成個 section 嘅 depth 咯，係嘛？咁即係個 neutral axis 一定要喺中間咯。如果你 mobilize 晒成個 section 就太多啦。So in that case, actually the neutral axis will be within the concrete sections. Okay, that's the case. And then the other case is that actually RS is larger than RC. That means the tension capacity will be larger than the whole compression capacity of the concrete. That means actually the neutral axis must be within the steel sections. So that part of the steel will also be in compression. So RS must be larger than RC, and in this case has to be larger than the RW. That means this is the compression force within the web. And then for this case, of course, actually RS also larger than RC. And in this case, is actually RW larger than RC. That means the web capacity is larger than the concrete capacity. In this case, actually the neutral axis will be within the web. Okay? So we just need to check RC is
provided that RS, that means the neutral axis will be within the concrete flange. If RC is smaller than RS but larger than RW, belongs to the second case, while actually RW is smaller than RC belongs to the third case. OK， 咁啊睇下 RS、RC 同 RW 咧，邊個大啲，邊個細啲啦 ？OK。Because the overall compression capacity will be equal to 0. So the moment is actually the compression and then times the moment arm, okay? But so actually this is some derivation of the equation. But for this one I will skip it because I think you will not memorize the derivation. 條式點樣 derive 出嚟咧？我就同你高呼啦。如果你有興趣咧，你可以睇一睇，同埋你想傾下嘅可以嚟同我一齊傾。但係咧，因為我覺得你唔會記得嗰啲 equation， 所以咧我就同你去高呼個 derivation 啦。但係咧，佢 in general 個意思咧就係 compression、tension 兩個等於，然後乘翻個 moment arm。即係將呢個 compression force 乘翻個 moment arm 就係嗰個 moment capacity。咁呢個好合理嘅。呢個亦都係你睇到上面個 compression。咁下面呢個 RS 咧就係成個 section 嘅 tension 啦。RC 乘2Z1，再加兩個 RSX 乘2Z2，就係個 moment capacity。呢個亦都係啦。呢個咧 RS2。呢個係 RS2 兩個啱啱喺中間嚟嘅，咁咧呢個就係本身個 steel beam 嘅腰嘅 moment capacity， 再加上呢個 RC 同呢個 RC 兩個係相等啦，乘翻佢之間嘅 moment arm 就係個 moment capacity。OK， 個意思個 physical meaning 係咁樣，但係我就唔同你去高呼個數學啦，因為最後你都係代落去，所以我就唔同你高呼啦。OK。So the equation is actually derived from using the compression times the moment arm, and then you can get the moment capacity. And then when you go for your exam, you will have this equation, okay? So you have this RS. RS means this is the tension capacity of the steel section, and then D actually is the overall depth of the steel beam, and then DS actually is the depth of the slab, and then the compression capacity of the concrete. Okay? So you just substitute all the values in this equation, then you can get the overall moment capacity of the steel beam. Okay? For the second case, is that the neutral axis is steel flange. So you have RS times D divided by 2, and then you have RC times DS plus DP divided by 2, and then you have RS minus RC times T. This T is the overall, the depth of the flange, and then divided by 4R SF. RSF, we can go back to this equation. To find RSF here, which is equal to BY, PY times the BT. So this RF is this one. Okay. So for these three equations, actually you can just substitute and then you can find the moment capacity. Okay. And then for the case of the web, then of course you can use this equation, okay? MC is the composite bending moment of this section. MS is the moment capacity of the steel beam. RC is the compression of the concrete section. D is the overall depth of the steel beam. DS is the depth of the slab. DP is the step of the trough, okay, the section. So you can just use this equation. Once you define the location of the neutral axis, then you can find from the answer. So I think we have this section before, And then we can take a look what is the moment capacity of this composite beam, okay? So to define which equation to be used, we need to find out what is the values of RC and what is the values of RS. So for here, actually, for the RC, it is equal to 0.45 FCU times the width of the beam. So width of the beam here is equal to 3000. And then you have ds minus dp. ds is equal to 140. And then dp is actually equal to 50. So you just substitute here. And then you find that it is equal to 3645. That means the concrete compression capacity, which is equal to 3645. Well, the tension capacity of the steel beam is equal to the area of the steel times the yield strength of the steel, then it is equal to 3P58. So you can see that the concrete capacity is larger than the steel beam capacity. So if it is the case, you can check which equation to be used. 如果咁樣 RC 大過 RS 咧，我哋咧就去咗第一個 situation，RC 大過 RS 係咪？ Then is RC larger than RS, then we will use the first equation. Then we'll use this equation to find for the answer. Okay? And then we can go for the equation. You can see that you have RS d over 2 plus ds minus RS over RC, ds minus dp divided by 2. So you have RS is the steel area, and then, steel capacity, and then 457 is the overall depth. This is 140 is the slab depth, and the RS is the steel capacity, RC is the concrete capacity. You have ds minus dp, so you have the equation. From that, you can get 1090 xknm. Now, of course, in the upper part of the calculation here, we try to do it by using first principle. But as I think in the exam, we are not going to use first principle, so I just let you to read it at home. Okay, if you want to take a look. So for this part, you can read it at home. It is not difficult. But as it is not within the exam, so I will just leave it for you, and then you can take a look when you are at home. Okay. So you will use this equation during the exam. So mainly, we will try to use this equation, and then you need to know how to substitute the values here and to find the moment capacity. Is it okay?我頭先可能唔記得咗俾個 break 你哋，你仲想唔想 break 啊？定係想講到40零分就走啊？Okay. Then we continue. 我頭先唔記得咗俾個 break 你哋，講得太興奮嘅就。Okay. Then I will let you go a little bit earlier. Okay. Instead of a break now. Okay. Now for the shear capacity, actually you can use 0.6 times Py times Td. Okay. So we can use this equation to check for the shear capacity. And then remember that if the applied shear does not exceed 50% of the shear capacity, then there's actually no reductions of the bending moment. 即係咧呢樣嘢咧係 still 係有啲唔同嘅，因為石屎我哋成日都 shear 同 bending moment 分開諗嘅 ，shear 唔會影響 moment， 即係你個 shear 加到幾大都好啦，個 moment capacity 都係咁多嘅。但係 still 佢唔係咁諗嘅。如果 still 個 shear 咧係大過50% 嘅 capacity 嘅 shear 嗰個 section 嘅 capacity 嘅話咧，佢係會影響個 moment capacity。OK， 咁 then if you have in this case actually you have to reduce your moment by using these equations. Now this is I just would like to remind you that steel will have this kind of behavior. Okay, but luckily in the exam we will not have this case. Okay. But I just like to remind you that actually the moment capacity will be resisted by the applied shear force. If the shear force is larger than 50% of the shear capacity of the steel beam, actually the moment capacity will be affected. So this is what I would like to mention to you and remind you once you have this kind of situation.
you can get back to the core of practice and can find a reduced bending moment. Okay? And then for the shear connectors, as I mentioned, we will install the shear connectors at the steel beam in order to make sure that the concrete and then the steel beam they do not slide against each other。因為如果石屎同埋鐵之間佢哋唔係即係連繫得好好嘅話咧，大家可以互相跣。點解會跣咧？你其實屈嘅時候上邊係撳佢，下面係拉啊嘛。如果你中間唔鎖死佢嘅時候，一撳過去嘅時候，佢咪向呢邊跣過咯。咁如果佢向前跣嘅話，其實你個 compression 係剔唔到喎，因為你向前推嘅話，佢向前行嘅話，咁你咪剔唔到 compression 咯。你點樣先可以形成嗰個 bending moment 係上面 compression 下面 tension 啊嘛？係咪先？你要鎖死個 section， 我推佢嘅時候佢剔到，拉佢嘅時候佢剔到，你先 form 到個 moment 啊嘛。如果我上面推下面拉嘅時候互相跣嘅，咁邊係有 moment 係嘛？你個 couple 都冇，即係你 couple 係要一個推一個拉先形成嗰個 moment 㗎嘛，可以運動嘅手喎，係嘛？你先一個推一個拉，你先至可以有個太極圈喺度㗎嘛，係咪先？咁如果呢一個推一個拉都形成唔到呢個圈嘅，係嘛？咁你咪冇個 moment。So we have to make the sections to be fixed, so that the upper part can take the compression, the lower part can take the tension. Then you can form the bending moment. Otherwise, if they slide against each other, then you have no composite action can be formed. Okay. So for here, actually, if I compress it, then if the slab can take compression, well, I tension it can take the tension. So I have to provide enough shear stuck to lock the section so that they can not slide against each other. So at this condition, actually, the design have to be considered how many of the shear stuck to be provided. Now each shear stuck actually can take the shear actually equal to PK. You can see that K is actually the characteristic horizontal load, P. And then depends on the location of the shear stuck. If it is in the positive bending moment, that means it's in the span, then you need to multiply by a factor of 0.8. If it is at the support, that means it is a hopping moment, then you need to multiply by a factor of 0.6. Okay? But the shear stuck itself actually depends on the height. Shear stuck will be applied on top, and then you have a height here. The deflection. So you have protection. It's actually the height of the shear stuck, and then you have the nominal shank diameter. You got the stuck here, something like that, and then the nominal height is actually then the stuck can be 16 up to 25 mm, while the nominal height usually is 70 to 95 mm. And then depends on the concrete strength that will cast with the stuck, then actually the so-called the shear capacity will not be the same. So it can be 111.4, 89.9, 67.1, 47.5. So the stuck itself actually can resist the shear force like that. 佢哋咧，如果要試個 shear stuck 咧，佢係攞個錘要包住幫我支 shear stuck，卡佢落出嚟。嗱，我嚟試個 shear stuck 咁樣。Then for this one, actually you have the P. We can call PK. So I don't know why they use the word PK here. Anyway, this is the characteristic
capacity of the headstock, okay, for the case here. But and we will multiply with this reduction factor 0.8, and then depends on the number of stock they will apply. Say if you just provide one stock or you provide two stock, there are further reduction factor for that. The BR is actually the average width of the concrete width, and DP is the overall depth of the profile steel sheet. Sometimes we will do one shear stock. Sometimes, depending on the situation, we will do two shear stock. Okay, so this one is 2, and then the K value is not the same. So this is actually the width of the top. This is the width of the top. The width of the top. So you have DP, and then you have PR, so that's the PS and then H is the height of the shear stock. So you have BR is the width of the trough, DP is the depth of the trough, and the H is actually the height of the stock. Okay? Then this equation can be another reduction factor that will encounter the reduction of the shear force within shear capacity of the shear stock. Now for the section, actually how much shear will be taken? Now when you have RC on the top and then RS on the bottom, then actually what is the actual force within the shear stock?嗱，如果上邊係推係 RC，OK， 下面拉係 RS。頭先我都講 RC 可能會大過 RS， 或者 RS 可能大過 RC， 係咪？如果個 case RC 係大過 RS 嘅話，即係我如果 mobilize 成個面嘅石屎係大過 mobilize 成個面嘅鐵嘅話，咁你話我上面實推嘅力係幾多？我 mobilize 成個石屎面嘅力係 RC。mobilize 成個鐵腳面嘅時候係 RS 點算咧？如果 RC 係大過 RS， 即係我 mobilize 成個石屎推嘅力係大過拉嘅力嘅話，咁我實際上喺上面推嘅力係有幾大？實際上喺上面推嘅力係 RS 啦定係 RC 啊？因為係 RS 咧係成個面。成個石屎面我 mobilize 晒嘅話就係 RS。RS 咧就係我成個鐵嘅面 mobilize 晒就 RS 咁多。譬如假設上邊係100下面80先算咧，咁會唔會同時上邊100下面80咁樣存在？唔會啊嘛，係咪？點解唔會啊 ？compression 定嘅 tension 嘛。咁所以如果上邊 mobilize 晒100，下面 mobilize 晒80。咁實際上邊係幾多啊？喺度80咯，因為上面等於下邊啊嘛，你上面 mobilize 全晒噶嘛，所以如果 RC 大過 RS 嘅話咧，上面實推嘅其實係 RS， 因為兩個一樣。Okay? So the case RS is larger than RC, then of course on the top is RC. Okay. However, if in the reverse, RC is larger than RS, then actually at the top, actually the force is equal to RS。明唔明我意思啊？如果上面係80，下面係100，咁應該上下都係80啦，係咪？如果下面係80，上面100，都係上下都係80㗎嘛。所以80係上下都冇上 ，OK。所以你只係 mobilize 好細嗰個啫 ，OK。如果 RS 大過 RC， 你咪 mobilize 咗 RC 咯。如果你 RC 大過 RS， 你咪 mobilize 咗 RS。即係只係可以 compression 同 tension， 只係可以細嗰個出現嘅啫嘛。你大啲嗰個永遠都 mobilize 唔到嘅，因為佢平衡唔到嘛。OK。So for this case, actually depends on the force that you have in the concrete. Say you have RC, then you divide by the capacity of the shear stock PE。嗱，假設你100，你每一條 shear stock 可以剔10，咁你咪要擺10支喺嗰度咯。咁你先至剔到晒所有嘅 compression 推落個石屎度，平均要俾10支 stock，你先可以剔晒成個 compression force。OK？ Because you need to remember compression is in the concrete sections, tension is in the steel section. If in the compression you have 100, each stock can take 10, then you need to arrange 10 stocks right there, right? So this is the concrete capacity, and then this is the tension capacity. Okay. Of course, if you can provide enough shear, enough shear stock, then you have the so-called the full shear connections. That means you can mobilize the moment capacity of the composite sections. But in case you do not provide enough number of shear stock, then you have the so-called the partial shear connections. 頭先假設你應該要 provide 10粒㗎嘛，係咪？但係你而家只係 provide 得8粒。provide 得8粒咧，你可以 mobilize 嘅 moment 一定係細啲嘅，係咪？因為你上邊你 take 唔到咁多 compression， so your moment capacity will be reduced. Now, if you need 10, but you just provide 8, that means you can just provide some compression in the concrete, right? But not the full compression in the concrete. So the moment capacity will be reduced. So we can call that one as the partial shear connections. 如果要10支先剔得晒嘅，你話我就剔得8支啫，咁你咪就係剔到之前嘅80咯。咁你個 moment capacity， 如果你照推嘅話，咪即係剔得翻之前嘅80咯。OK， 你落少啲，你落少20%，你就當一陣間我會同你講點計啦，佢就會剔少20%。OK， so that is actually depends on the number of shear stock, then your moment capacity will also be reduced. Now R is actually the force within the concrete, RC, okay, or RS. If you put less shear stock, that means the shear force in the concrete will be smaller. It can be equal to RQ, okay? I don't know what is Q, but I just know that the compression within the concrete will be smaller. The value is equal to RQ, okay? Then P is the shear capacity of the shear stock. Then NP is the number of shear stock that I put less right there. Then for here, the force divided by 0.45 FCU, and then the width, I know the neutral axis depth for the composite sections. So again, I know the neutral axis of the composite section. So one is actually within the concrete flange, and then the other one actually in the steel web. So I can use these two equations to find for the capacity. It's the same, okay? But usually we will not use this kind of exact equation. 嗱呢個咧真係 exact 嘅，我擺少啲 shear stock，因為每一條 shear stock 我知道佢嘅 capacity 係幾多。譬如我擺10條，我咪照乘翻個 capacity， 我咪知呢個 RQ 係幾多。咁我知呢個 RQ 係幾多，我照除0.45 FCUB 咧，我知個 neutral axis 係幾多。咁咧我就可以知道 neutral axis 之後咧，我就可以用第一或者第二條式嘅 ，OK？ Now this is the case. But usually we will not use this one because it is more troublesome, or you need more procedure to substitute in these equations. Instead, I will use this way to calculate. Say for example, originally I need to put 10 shear stock. Right now I just put 8 shear stock. Then I have this K, this one is the degree of shear resistance. Say I just put 0.8, or by the passing here. Then how can I know the shear capacity? I mean the moment capacity. Now originally, I have this equation. 嗱頂嗰條式咧，頭先我咪有兩條式嘅，係咪？頂嗰條線咧，就用我頭先 exact 嗰條 equation 計嘅。It is very exact. But the bottom here, this connections，即係話咧，我呢度擺咗幾多嘅 shear stuff 落去。The vertical one is the moment capacity. So you can see that you have the x-axis and then you have the y-axis. When I don't have any shear stuff, no shear stuff, what is the moment capacity? 如果冇 shear stuff 嘅話，你屈呢個 composite beam，你屈到啲咩？成日屈到條 steel beam 咯，你石屎冇幫手嘛。So if I have no shear stuff, the moment capacity will be just the steel section. If I have full shear stuff, then I will have a full composite capacity, right? So in between, I just put a straight line here. So just depends on the number of shear stuff applied. I can, proportionally, I can get more moment capacity. Okay? That means I have no shear stuff is here, I have full shear stuff is here. If I put 50% of the shear stuff, I get 50% of the moment capacity. Okay? If I put 80% of the shear stuff, then I get 80% of the moment capacity. 即係話咧，佢將 composite 嘅 moment capacity 同埋就係 steel beam 嘅 capacity 呢兩個相減嘅話咧，就係呢兩個 difference。因為你完全唔加 shear stuff，你都可以屈到條 steel beam 噶嘛。你冇 shear stuff，你都係屈到條 steel beam 喺度噶嘛。你加咗 shear stuff 俾佢，你就 mobilize 個 full 嘅。而 between 個 line 直線俾佢，即係按比例。So MC minus MS is actually the difference between these two moment capacities. Then this K is actually how many percent of shear stuff have been provided. And then plus this MS. MS is like here. Okay? This one is very simple. This one actually is MC. This one is MS. So when you have full, you have this one here. When you have no is here, you just draw a straight line. Okay? So basically, this value is equal to MC minus MS. This is the full moment capacity. This is the shear capacity, but this is steel capacity. Okay? So this is the value K. This is equal to 1. This is equal to N. So if you have no K is equal to 0, then moment is equal to MS, right? Okay? 0, and then this is MS. This K is equal to 1, then the moment capacity is equal to MC. If it is equal to 1, then the moment capacity is equal to MC. In between, say from here, then this is 0.5. Then it's simple because MS plus 0.5 times MS MC minus MS. And this is the moment capacity. Okay? So this is simple. 你冇都有 MS 㗎啦。如果有0.5咪加翻個 difference 嘅0.5。Okay? So this we call the simplified method. This is what you have in the base. And then this is how much you provide. And then this is the composite portion. Okay? 即係你加冇你咪攞足個 composite portion，即係 composite。你加50%，咪攞50%嘅 composite portion。咁呢個係好合理。 then you may ask why we have two methods. Now, usually this one is easier to calculate and then quicker. If this capacity already can fulfill your requirement, then it is okay. But if you think that, or if you find that the capacity is not enough, then of course you can use the exact notation to find there is some room for it. Okay? 如果唔夠嘅，你用翻 exact equation check 去做可以加少少。但係可能呢個呢個嘅消題嘅方法你已經搞掂，咁你搞掂。OK？ Now here actually is for the case for some point loads. So if you have some point loads, I would just like to mention that your shear stuck actually may not put in an equal distance. Okay. So actually for here actually is the case when there's some concentrated load, then this indicate how you would put the shear stuck at different locations. And then there are some detailing. I think I will stop here after talking about the detailing. Okay. Now for the shear stuck here, you can see that usually the longitudinal spacing of the shear connector, they do not exceed 600 mm or 4ds. That means the shear stuck actually will put along the steel beam. Usually the spacing will not exceed 600 mm for 4ds, where ds is the overall depth of the slab. 即係我向住條邊個 direction 咧，唔會過600 mm。The minimum center to center spacing of the shear stuck is 5D along the beam and 4D between adjacent stuck。即係個最低嘅 distance 咧係5個D，而佢兩個之間嘅距離咧係4個D。OK，D 咧就係個 shank diameter，即係嗰個